Hello and welcome to today's lesson where we're going to look at questions for practical skill styles questions in AQA A-Level Physics. So in today's lesson we're primarily going to focus on how we can answer extended questions which relate to the practical skills required for AQA A-Level Physics. So let's have a look at a couple of questions. In this question it says figure 3 shows an unknown mass m hanging from a bar. The bar has negligible mass. The bar is freely pivoted at one end and is supported by a vertical spring fixed to point P. The support is adjusted so that the bar is horizontal. The spring obeys Hooke's law and has a stiffness of 25 newtons per meter. Distances big D and small d are shown in figure 3. We need to prove that big M is equal to 25 big D delta L over dg, where delta L is the extension of the spring. Well, you look at this type of question and you think to yourself, what's been going on? Well, firstly, we've got the idea of Hooke's law going on, so we need to relate to that particular question, and we've also got a pivot which is attached, a bar which is attached to a pivot. So what we've got to do is we've got to look at what the forces are in this situation. Now if we look in this situation, we know that mg times by d is equal to t big D. Now let's think about why this is. Now we know in this particular example that T is going to equal K delta L because we're looking at Hooke's law. Now we could also write that as 25 delta L because K is going to be 25 in this particular example. Now we also know that mgd is equal to TD. How do we know that? Because we can look at the particular moments going on in this situation and work it through like that and equate the two as such. So the tip is with practical skill styles questions, they will try and get you to apply your knowledge to different situations and prove equations based on the situation you are given. Now the next type of question says describe how you would use this apparatus to determine the value of big M by a graphical method. Now in your answer you should include details of additional apparatus, the measurements made, the detail of the procedure and the graphical determination of M. Now let's look at where you get your marks from. So we'd use a meter ruler to measure big D as it's a length. Then for 6 or more values, remember you need at least 6 or more values to gain a accurate line of best fit which you are confident in. You would then measure D and delta L. You then adjust the support so the bar is horizontal each time, or you can check the bar is horizontal by using a spirit level or that the spring is vertical. You would then plot a graph of delta L against D and draw a straight line, measure the gradient of the line, then you can equate this to the values to find M. Now it's very important as you look through this particular example question, you look at the situation and you go to yourself, right, how would we alter this situation to get readings? Now again, like I mentioned before, it's very unlikely in a question you will be given an experiment which you've actually done in class. The point of these examination questions are to test your transferable skills. So they'll want you to interpret a diagram, interpret information and work out how you will plan a method successfully. Now it's my tip that for an experimental method, you state what will be varied and how it will be measured, so you'll identify your independent and dependent variables. If possible, include values and how many values you would take for that. State what will be measured and how it will be measured, so in that instance what measuring device would you use. Include good experimental technique. Now again, you've got to look at the situation. So in this situation it was clearly very important that the bar was horizontal, so that's our good experimental technique. Then where feasible, discuss the idea of repeats, then indicate what graph will be drawn with the results that you would obtain, and then finally how the value or relationship you would like to be determined in the question is worked out from the graph. So in this instance you wanted to work out big M, so you look at the equation given previously, you would then relate that to the graph that you would have drawn and then work it out via that methodology. Now, another question which could be asked is as follows. A set of LEDs emitting lights of different colours was used. The current PD curve for each LED in the forward direction was plotted and Vmin, the intercept on the PD axis, was recorded. The results are given in the table together with the average wavelength and frequency f of the radiation from the LEDs. Now, Firstly, use c equals f lambda, where c equals 3 times 10 to the 8th meters per second to complete the table. Now again, when people are doing this, if you're not looking very carefully, you'll not realise that the frequency is given is times 10 to the 14. So you've got to be wary of that when you're recording your results. So what you would do is you would say that f is equal to c over lambda. You've got lambda, and again, look at the column, it's in nanometers, so you're going to have to convert that into meters by times it by 10 to the minus 9 and then working it through as such. So you get an answer of 5.31 times 10 to the 14 and 6.38 times 10 to the 14. You would then complete your graph by plotting the missing 2 points and drawing a straight line of best fit. Now again, to get your marks in A-level physics, you've got to make sure both points are correctly plotted to the nearest millimetre, and then you draw a well-drawn straight line of best fit. Now you'll notice in this one that there's an anomalous result which you've got to be able to identify. They do tend to put that into questions on occasion to test to see your line of best fit drawn abilities. And as a good line of best fit should, it should follow the trends of the points, obviously not the anomalous one, with an even scatter of the points on either side of the line. Then you determine the gradient of the graph, and then a triangle is drawn, a gradient triangle, and then you would have it at least 8 centimeters in length. It's obviously going to be a fair size, so you get a valid result. So you consider a fair number of values, and you get a gradient in the range of 0.44 to 0.46, given it either 2 or 3 significant figures as per the question. Now, here's a bit of a tip when you're working out a gradient. Firstly, draw a large gradient triangle on the graph. The mark scheme said at least 8 centimeters. Take care on the units and the prefixes indicated on the axis scale. So look here, you're going to have to be careful regarding using nanometers and times 10 to the 14 hertz. Always show your calculation in your answer. So show literally delta y over delta x, and then include the unit on the value. And the trick is, if the line is sloping downwards, the gradient always has to be a negative. Now discuss the reliability of your value for your gradient. Well, you could say that the anomalous point will make the value less reliable, because you would argue that some points are not close to the line of best fit. However, if you've ignored this anomalous result and all the points are close to the line of best fit, this indicates you're confident in your line of best fit and you're confident in your trend. So that means you're confident in your gradient, suggesting the value is reliable. Now, this next one is an interesting one, because we're told that theory predicts that the energy lost by the electron in passing through the LED is the energy of the emitted photon. EV equals HF, where H is Planck's constant and E equals 1.6 times 10 to the minus 19 coulombs. Find a value for H by using the general equation of the straight line, y equals mx plus c, and your answer to 3.3. So you've got to recognise in this situation that the gradient in your graph is going to be H over E, because if we look at the values given, we know that if we rearrange this particular equation, we know that V over F is going to equal H over E. So when you do your gradient of V over F, it's the same as H over E. And we know what E is. We know E is 1.60 times 10 to the minus 19 coulombs. So therefore, to work out what H is going to be, it's going to be gradient times by E. So you'd work it through like that and get an answer out. Now again, as you'll be aware, Planck's constant is 6.63 times 10 to the minus 34 joule seconds. Now you notice in the answer it's between 6.95 to 7.44 times 10 to the minus 34 in your accepted answers. They do tend to do this in examination questions. They tend to work out a value which is not the exact answer, which is the accepted value. That's to stop students just writing down the accepted value as the answer. Now it says the next question, the accepted value, like I mentioned before, is 6.63 times 10 to the minus 34 joule seconds. Calculate the percentage difference between the value you calculated in 3.5 and the accepted value. So what you would do is you would find the difference in the two values. So whatever value you calculated, subtracted by 6.63 times 10 to the minus 34. You then divide it by the accepted answer, 6.63 times 10 to the minus 34, and you times it by 100 to get your percentage difference. Now, just to clarify, for an equation question, when you look at a line of best fit, which is a straight line, you place the equation of your graph or of your experiment into the form y equals mx plus c. Look at what is placed in the x and the y axis of your graph. You can then find the y-intercept and the gradient from your graphical values, and if you've got constants in values, ensure they're used in your calculations as well. So that's a very important idea. Now, in this next question, question 3 here, complete the table. Now, the trick is here, we're looking at both height in millimeters. Now, how do you work out the mean height? Well, the mean height is going to be the answers all added up and divided by the number of answers you've added up. So it'll be 380 plus 384 plus 379. All added up, then divided by 3 to get your mean height. Now remember, we're going to give it to 3 significant figures and no decimal places, because that's what's given in the other particular values in the column. And then to work out the natural log of h, what you would do is, in your calculator, you would press the natural log button, you'd input the value of the mean height from the question, you then close your brackets, equals in the calculator, and you get your answer out as so. Again, you'd plot your points within 1 millimeter and draw an accurate line of best fit as a straight line with an even scatter of points on either side. Again, that's been made very clear in these two questions that your line of best fit should be a straight line through with an even number of points on either side of the line. And then you work out your gradient by once again drawing a triangle with at least a side of 8 centimeters on either one, and then using that to work out the gradient. Now again, it says the correct answer is between minus 0.0140 and minus 0.0138. Now the minus would indicate to me that the line of best fit must be sloping downwards, because a negative gradient indicates the line of best fit is sloping downwards. So like we mentioned before, for a gradient, draw a large gradient triangle on the graph, take care on the units and the prefixes indicated on the axis scale, clearly show your calculation when you're working out the gradient, include the unit in your answer, it's the units of the y-axis over the units of the x-axis, and if our line is sloping downwards, we've always got to give our gradient as a negative. Now the next question says, theory predicts that the relationship between h and t is given by the equation small h equals big H e to the power minus lambda t, where big H and lambda are constants. State the value for big H and lambda with their units. Now in the previous question, we had plotted on the graph natural log h against t, and then we can use this to work out our values. So what are we going to do? Well, big H is 665 millimeters working through, and then the lambda is the answer to the previous question without the minus sign, and our units are seconds to minus 1. Now you might think to yourself, where on earth have those numbers come from? How have you derived those numbers? Well, it's very important that for a natural log against time graph, the multiple on the right hand side of your exponential equation, in this example, big H is the y-intercept. So that 665 was the y-intercept of our log h against t graph. Now it's going to have the same units as the y-axis, which was millimeters. Now the other thing to realize is that the power multiplied by the x term is going to be the gradient of the graph. So what was our x term in our log h against t graph? Well, it was t. So the term in the exponential, which is multiplied by the t, lambda, is going to be the gradient of the graph. Now this makes sense because it's a negative value and the gradient is sloping downwards. So again, we've got two negatives here, which is why we'd remove the negative sign when we're working out lambda. And therefore, what's our unit going to be? Well, our unit is going to be the unit of the gradient. Now this is going to be very, very important, because why, you might say the units in the question were given as seconds to minus 1. Well, why were they not given as millimeters per second? Because it's y divided by x. Well, the important thing to note is that when you put a natural log on a term, such as log h, it removes the unit, so it no longer has millimeters as its unit. It becomes a unitless term. The natural log is just a mathematical idea. It has no physical reality, so as a result there's no units, so it's going to be no units on the y divided by seconds on the x, so it becomes seconds to the minus 1. Now it says suggest a possible source of systematic error in the Burette experiment and explain whether this would have affected the value you found for lambda. Now if you look at this particular experiment, the systematic error, which is a constant error in every measurement, is most likely going to be in h, the height. So you might have made a mistake when you set up the height of your burette. Now consider the effect of the natural logs being plotted. Now it's unlikely to affect the gradient for a couple of reasons. Number one, if it's out by the same factor for each term, well therefore it'll have the same impact on all the results, so therefore won't affect your gradient. And also, since h is numerically a very, very large number, therefore it's unlikely to have a big effect on it because the change in the gradient is going to be very small. Now suggest a source of random error for this investigation. So a random error is most likely to be associated with the time, because you will have a reaction time from the human measuring the time it takes to empty the burette. So that means that that's most likely going to be random, because that's going to vary from result to result. Now the best way to minimize the impact of a random error is to repeat the readings, and so therefore repeating the readings will minimize your random error, or reduce random error, so the effect would be minimized. And you know the effect is minimized because in the question it tells you that 3 repeats have been taken, so it's unlikely that the random error would have had a significant effect because the repeats will have reduced that random error. Right, now in this next question, again, similar to what we've done before, it asks you to complete table 1. So when you're completing table 1, you need to look at the values and work them through. Now just please note that in t squared, we're giving our value to 2 decimal places. So you should give your value in your calculator to 2 decimal places. And it's the same for t squared h, and then h squared is to 3 decimal places. So you give your answer to that and you work it through as such. You then plot your points and draw your best fit line in there. So again, like we mentioned before, both points are plotted within 1 millimeter. An accurate best fit straight line is drawn with an even scatter of points on either side. Determine your gradient. Like we mentioned before, a gradient triangle is drawn with at least sides of 8 centimeters, and correct values are read from the line of best fit. You then give an answer for your gradient. In this example, it's between 3.90 to 4.06. So again, like we mentioned before, for a gradient, you draw a large gradient triangle on the graph. You take care on the units and the prefixes indicated on the axis scale. You show your calculation very clearly. You include a unit on your value, and if the line is sloping downwards, you ensure the gradient is given as a negative. Now show that the gradient of the graph in figure 2 is 4 pi squared over g. Well, we know from the question we are given the equation for t. So what we would say is you'd say t squared h equals 4 pi squared h squared over g plus 4 pi squared k squared over g. Now how do we know this? Well, we know this because we're taking the terms through and working it out. So what have we done? We've squared both sides of that original equation. So we've got t squared equals 4 pi squared, because 2 pi squared is 4 pi squared, going to be times by k squared plus h squared over gh, because the squaring has removed that square root term. At that point we can take h to the other side, so we can say t squared h is equal to 4 pi squared k squared plus h squared over g. We've then separated it out as such like that. So we've now got it in the form of the equation y equals mx plus c, because if you notice on the graph that was drawn in the previous question, the y-axis is t squared h, and the x-axis we will note as going to be let's get this right, it's going to be h squared. So as a result, that tells us as y equals mx plus c. We know that m is going to be what is times by times by, that value of h squared, so it's 4 pi squared over g, and indicating to us that 4 pi squared k squared over g is going to be c. Now use g to then calculate g using your answer from 4.5. So what you then do is you work out what the gradient is from the graph. You say it equals 4 pi squared over g. You rearrange that to make g the subject, and you work through your answer. What does the intercept on the line of the vertical axis represent? We've just mentioned it. That is then going to be the plus c in your term. So it's very important that you can, when you're given a graph which you can draw a straight line of best fit with, you always try and get your equation in the form of y equals mx plus c. Then state the unit for constant k. So what we can then do is, if we know what our intercept is and we know what the unit of the intercept is, we can then work out things based from that, and it works out to be the meter. So we can work it through as such like that. Now it says here, using the data in table 1, the percentage uncertainty, determine the percentage uncertainty in the largest value of t, and the precision in each measurement of h was 1 millimeter. So what we do is we can take our precision or our resolution for time, and we do our absolute uncertainty, which in this instance will be the resolution or precision of the instrument for time. We then divide it by the largest value, times by 100, and we get 0.22%. We do the same for h, and we know it's 1 over the value, which corresponds to the largest value of t. So if we go back to our graph, we find our largest value of t, and we can work it through in such like that to find our largest value of h, or the equivalent value to h, I should say, sorry. We do that, we times by 100, and we get our answer to be 1.0%. Now we know, assume the percentage uncertainty in g is the same as the percentage in t squared h for the largest value of t. Calculate the percentage uncertainty in g. Well, if we know the percentage uncertainty in t and we know it in h, and we've got to do t squared h, we can work it through as follows. When you multiply two terms in an equation, you add their percentage uncertainties, and if you have a power in your equation, you multiply your percentage uncertainty by the power. So because t is t squared in this particular example, we would do 0.22 times by the power, which is 2. So it'll be 0.22 times by 2, which is 0.44. We then would add it to the percentage uncertainty of h, because you're multiplying t squared by h, so we get our answer of 1.44%. So remember, for percentage uncertainties from a set of repeats, absolute uncertainty is the range of results divided by 2. Then you can use the equation percentage uncertainty equals absolute uncertainty over value times by 100, and you give the same no decimal places as the values in the table. When you're combining percentage uncertainties, when it's a times b, you add the percentage uncertainties. When it's a divided by b, you add the percentage uncertainties. And when it's a multiplied by x, you multiply that power of x by the percentage uncertainty. Now the accepted value of the gravitational field strength in the UK is 9.81 newtons per kilogram. Calculate the percentage difference for the value you found in 5.5 and the accepted value. Now, like we mentioned before, how do we calculate percentage difference? Well, it's the difference in the accepted value and your value divided by the accepted value times by 100. Then discuss whether the experimental value for g agrees with the accepted value. Now it's very, very important to note you've got to look at your percentage uncertainties you've calculated and the percentage difference you've calculated. Now if the percentage difference is smaller than the uncertainty, that tells us that the experiment agrees with the theory, it agrees with the accepted value, because the uncertainty gives you the range of the results could lie in. The difference tells you how far out you are. So if your uncertainty was 10% but you had a difference of 5%, that tells you that when you've considered the uncertainty, the two values are going to be the same, so it's accepted. So, as a tip here, to calculate a percentage difference, the percentage difference is the difference in values divided by the accepted value times by 100. And if you want to determine if a value is valid, you've got to understand the percentage difference is smaller than the percentage uncertainty. And they're key things to remember when you analyze data in A-level physics. So I hope you've enjoyed this lesson, looking at some examples of practice questions for practical skills in AQA A-Level Physics, and have a lovely day.